Swayam Prabha. Digital India. Educated India.
Welcome back. So, in the last lecture we just talked about the different procedures by which you can measure the unit weight in the field. So, what are those procedures? What are those methods? First one was the sand cone method, then rubber balloon method and nuclear method. So, among these three we will be talking about the sand cone method, which is as per ASTM D1556. So, basically in the sand cone device consists of a glass or plastic jar with a metal cone attached at the tips, right. So, you will be having one jar which will be made of glass or plastic, and on top of that you will be having some metal cone. So, I will show you the figure how it will look like. So, now let the combined weight of jar plus cone plus sand. So, you will be filling some sand inside the jar. Now, the combined weight of the jar itself plus cone which will be attached at the top, and the sand whatever you have put inside the jar, the combined weight is say W1, capital W1. Okay. The plastic jar and the metal cone will look like this. So, this is the sand cone method device. So, as you can see, so basically this is the jar which can be made of steel, glass or say plastic, and this is the metal cone, okay, which will be attached on top of the jar. Now, you can put sand inside the jar, okay, and then the combined weight of the jar plus cone plus the sand whatever you have filled inside the jar. So, that say that is W1 whatever we have decided now. And now, in the field what exactly we are doing with this sand cone device. Now, in the field where you have compacted the soil and where actually you need to find out the unit weight. So, basically in the field you excavate a small hole, okay, very comparatively reasonably small hole you just excavate, okay, and say the weight of moist soil excavated from hole is W2. So, whatever soil you have excavated from the hole, say the weight of that moist soil is say W2, because you have compacted. So, the soil will be moist. So, now if the water content of excavated soil is known, which is possible, right. So, you are excavating the soil from the hole whatever you have excavated in the site, and then you are collecting the soil, and then you can find out the water content from the laboratory experiment. Then the dry weight of the soil is given by this expression, where W3 is equal to W2 whatever is already explained. So, as you can see here, so the weight W2 is the weight of the moist soil divided by the 1 plus small w, where small w is the water content which you have determined from the laboratory experiment by 100. So, if you express the water content in percentage, so it will be coming as W in percentage by 100. So, that will give me the dry weight of the soil. So, that is W3. Now, after excavation, the cone with the sand filled jar is inverted and placed over the hole. Sand is allowed to flow out to fill the hole and the cone. So, now what you do? So, you have excavated the soil, you have taken out the soil, and you have done whatever experiments are required to find out the water content and other things. So, that you have done. Now, in the you take the jar which is filled with sand. Now, you invert the jar on top of the hole, okay, excavated hole, and then you allow the sand to fill in the hole itself. So, now what will happen, the sand will come out from the jar, it will fill the cone as well as the hole. Now, based on that you will be getting some sand will be remaining in the jar itself, and some sand will be remaining in the cone as well as it will be filling the excavated hole. Now, if the combined weight of jar plus cone plus remaining sand, now whatever sand has gone out from the jar, so whatever is remained, okay, so jar plus cone plus remaining sand in the jar, if it is W4, then the weight of sand to fill the hole and the cone is W5, which is nothing but W1. What was W1? That is the combined weight of jar plus cone plus the total sand which was filled in the jar. Now, the W4 is nothing but the weight of jar plus cone plus the remaining sand. So, whatever sand has gone out from the jar and which has filled basically the hole as well as the cone, that is nothing but W5, which is equal to W1 minus W4, as simple as that. The volume of excavated hole is, therefore, the V is given by W5. W5 is the weight of sand which has filled the hole as well as the cone, minus WC by the gamma d sand, where WC is the weight of sand to fill the cone only, because W5 was the weight of sand which was filled in the cone as well as the hole. Now, if you want to find out the weight of sand which is filled only in the hole, then WC must be deducted or must be subtracted from W5. So, W5 minus WC will give you the sand which is filling the hole, divided by gamma d sand. If you talk about that is nothing but your dry unit weight of sand. If you divide the W5 minus WC by gamma d sand, you will be getting the volume of excavated hole. So, whatever hole you have excavated, the volume of excavated hole can be obtained by this expression. Then the values of WC and gamma d sand are determined in the laboratory. Okay. So, there is no issue, gamma d sand, that is the dry unit weight of the sand, it can be obtained from the laboratory experiment, and WC also you can find out from the laboratory. Now, the dry unit weight of compaction is given by gamma d, which is equal to W3 by V. Okay. Now, we will take one example. Now, we will be taking few examples on compaction topic. So, this is the problem 6. The problem says a laboratory compaction test on soil having GS equal to 2.68 gave a maximum dry density of 1.82 gram per cc and water content of 17%. Determine the degree of saturation, air content and percentage air voids. So, these all terms are known to you from the basic definition when we discussed in very earlier classes. At the maximum dry density, what would be theoretical maximum dry unit weight corresponding to 0 air voids at the OMC. Okay. So, these things we need to find out. So, we have few parameters and we are going to obtain those other things whatever has been asked in the problem. Okay. Let us start this problem. Okay. So, we have seen the problem, now we are going to solve this problem. So, problem 6, we know from our basic definition and we can establish the relations, that is gamma d is equal to Gs into gamma w. Already we have seen this expression earlier for several times. W, that is your water content, Gs by S, that is degree of saturation, right. This equation is, or this expression is known to me, or else you can establish this relation, there is no issue. So, here what are the things are known to me? Gamma d max, which is equal to 1.82 gram per cc, which is nothing but 18.2 kilonewton per meter cube. So, this multiplied by G, right. So, I am considering G as, for this problem I am considering G 10 meter per. Okay. So, in some problems we can G basically is 9.8. So, anyway, so for some simplification we are considering G equal to 10. So, there is no issue. So, gamma d max equal to 18.2, that is given in the problem, and that is happening at the water content 17%. So, gamma d max will always occur at OMC, right. So, the whatever water content is given, so that is nothing but your OMC, which is 17%, and your specific gravity of soil solid is given as 2.68. So, these are the parameters are given in the problem. Now, from equation 1 we get, so from equation 1 we get 18.2 is equal to 2.68 multiplied by 10, that is the unit weight of water, divided by 1 plus 0.17 into 2.68 by S. From this I can get the degree of saturation is equal to 0.96, that means 96%. Okay. So, by knowing gamma D max, so if you plot the compaction curve, okay, and then basically if you find out gamma D max and OMC, you can observe from the compaction curve, from this expression you can find out the degree of saturation. Okay. Now, therefore, air content which is given by AC, if you recall, we have covered these simple definitions, which was given by VA by VV, right, where VA was the volume of air and VV was the volume of voids, right. So, now AC, if you recall from the definition, it is nothing but 1 minus S, that is 1 minus degree of saturation, which is coming as 0.04, which is nothing but 4%. Okay. So, your air content is 4%. Okay. Now, we will be talking about the percentage air voids. Now, again it can be established that your gamma D, that is the dry unit weight of soil, is equal to 1 minus, what is Na? Percentage of air voids, right, into Gs into gamma W by 1 plus W G, right. So, this expression can be established from the simple definition whatever you have seen so far. So, gamma D is equal to 1 minus Na, where Na is the percentage air voids, into Gs into gamma W divided by 1 plus W into G, where W is the water content. Now, from this expression we can write 1 minus Na is equal to 18.2 multiplied by 1 plus 0.17, that is your water content, multiplied by 2.68 by 2.68 into gamma W, that is 10, which is giving me 0.99. So, therefore, Na is equal to 1 minus 0.99, which is equal to 0.01, which is equal to 1%. So, percentage air void is 1%. Okay. So, now basically when your percentage air void is say 0, that means your degree of saturation is 1. So, at that time you will be considering that 0 air void condition is occurring. So, when Na is 0, that is your S equal to 1, that means degree of saturation is 1, at that time your theoretical dry unit weight at water content 17% is given by, that means at 0 air void condition what is your gamma D, that means dry unit weight. So, that we are going to find out. So, at 0 air void condition your percentage air void is 0 and that means your degree of saturation is 1. Okay. So, is given by gamma d, which is equal to G gamma W 1 plus W into Gs. From this we can find out gamma d is equal to 18.4 kilonewton per meter, because we know all the values here. So, at the water content 17%, that is your OMC, your gamma d max, that is the practical or the actually observed gamma d max in the laboratory was 18.2, whereas the theoretical maximum is 18.4, which you cannot achieve, but this is the theoretical maximum which is happening at 0 air void condition. So, now we will take the next problem again on compaction. So, let us see the problem first. Okay. So, the next problem says the in situ void ratio of a granular soil deposit is 0.5. Okay. The maximum and minimum void ratios of the soil were determined to be 0.75 and 0.35. Now, Gs is equal to 2.67, determine the relative density and relative compaction of the deposit. So, basically we are going to find out the relative density and as well as the relative compaction of this particular soil. So, now basically your relative density, this is your problem 7, your relative density from the definition you know E max minus E natural by E max minus E mean into 100%. So, that is your, that is the expression for your relative density, and already we have established this relation and we have seen and we have solved a couple of problems on that. So, what is your E max in the problem? So, that is your maximum void ratio, which is 0.75, it is given in the problem. Now, what is E natural? What magnitude of E natural is given in the problem? The in situ void ratio, that means the natural void ratio of the granular soil is 0.5. So, that is given, divided by E max is 0.75 again, and what is E minimum? That is your minimum void ratio, which is given in the problem as 0.35. So, if you solve this calculation, you will be getting your relative density is 62.5%. So, your gamma d max will be G gamma W by. So, at what situation you will be getting maximum dry unit weight? So, could you please could you please tell me that what should be the maximum unit weight at what void ratio? When the soil will be densely packed. So, when the soil will be densely packed, at that time what should be the void ratio? E minimum. So, gamma d max will occur at E minimum. So, from this expression, so this expression is already known to me, or else you can establish that relation, there is no issue. So, in that relation your E value, that is the void ratio value, should be minimum, which will be giving me the gamma d max. So, if you put all the values 2.67 into 10 divided by 1 plus 0.35. So, that is giving me 19.78 kilonewton per meter cube. Similarly, if you can find out gamma d minimum, that is the minimum dry unit weight. At what situation gamma d minimum will occur? When your void ratio will be becoming maximum, that means loosest packing will be giving you the gamma d minimum. So, that is given by 1 plus E max. So, if you put the values, you will be getting 15.26 kilonewton per meter cube. Now, what is the value of gamma d in situ, that means in the field condition, that is Gs gamma w by 1 plus E in situ, which is nothing but E natural, right. So, if you put all the values divided by 1 plus 0.5, which will give me 17.8 kilonewton per meter cube. So, you have got the relative density as well as you have got the different unit weight at different condition. That means, when your soil is densely packed, at the time you have got gamma d max, which is equal to 19.78 corresponding to E minimum. Then you have got gamma d mean, that means when the soil is loosely packed or the loosest state, that means your void ratio was E max, and at that time you have got gamma d mean equal to 15.26, whereas at the in situ condition, at the natural condition, your gamma d in situ is coming as 17.8. Okay. So, now with that we can calculate the relative compaction. So, we can write down the relative compaction. What will be the expression for relative compaction? From the definition itself, we can see that whatever you have achieved and whatever was there, based on that you can calculate the relative compaction. So, that is nothing but gamma d in situ by gamma d max, or by, if you want to express that thing in percentage, multiplied by 100. So, gamma d in situ, that means you have achieved that much of compaction, whereas gamma d max, that is the densest packing available in the laboratory. So, in the laboratory basically gamma d max you can achieve, okay, but in the field you have achieved gamma d in situ. So, the ratio of these two will give you the relative compaction, and if you put the values 17.8 by 19.78 into 100, so which will be coming as 89.9%. So, you have achieved 89.9% compaction in the field as compared to the gamma d max available in the laboratory. So, I will stop here today. So, in the next lecture we will solve another problem which will be very important, and I mean there are several aspects, and that problem is basically talking about some practical problem or practical situation. Based on some practical situation we have developed that problem, and in the next class we will see that problem. So, today I will stop here. Thank you very much.